Welcome to the Explainer. So next time you're tossing out fruit peels in your kitchen, you might want to pause for just a second. Today, we're looking at a genuinely fascinating journey of scientific transformation. Imagine taking a massive, global source of agricultural waste and literally turning it into a highly effective, natural food preservative, something that could, very soon, be protecting the groceries sitting right there in your fridge. We're taking a lab-to-table look at a recent study on the mangosteen fruit, and we're going to explore how researchers are extracting heavy-hitting bacteria-fighting compounds from the exact parts of the fruit we normally just throw in the trash.
Okay, let's dive right into this. Our roadmap for this explainer tracks the exact scientific process used by the researchers. We're going to start by looking at nature's overlooked food protector, walk through the green extraction process, analyze how well this extract battles foodborne bacteria, take a peek inside its chemical cocktail, and finally, look at the absolute crucial safety check.
All right, let's kick things off with stage one of our scientific journey by looking at the raw material itself. So the Garcinia mangostana, or the mangosteen, is famously known as the queen of fruits because of its really delicious, sweet white flesh. But get this, a staggering 60% of the fruit's total weight is simply discarded. Think about that for a second. Globally, this accounts for about 17 million tons of agricultural waste every single year. I mean, that is a massive environmental and economic loss. But as scientists are now discovering, it's actually a massive untapped resource too.
The specific part of the fruit making up all that waste is called the pericarp. It's that really thick, dark purple rind on the outside. Now, traditionally, this pericarp has actually been used as a remedy for ailments like diarrhea, which tells us right off the bat that it holds some pretty powerful bioactive properties. Yet in modern food science, it's been wildly underexplored. The researchers behind this study basically looked at this massive pile of waste and asked, could this lead from ancient medicine into a modern food safety solution to keep our everyday foods safe from spoilage?
Let's step into the laboratory and see how scientists actually pull those beneficial compounds out of that tough pericarp. The researchers didn't just smash the fruit up willy-nilly. They used a very calculated, green experimental workflow. This flowchart brilliantly illustrates the exact sequence they used to process freeze-dried pericarp powder into a really potent liquid extract, testing different solvents and separation methods along the way.
The whole process relies on three relatively simple, energy-efficient steps. First up is maceration. Think of this a bit like brewing a highly calibrated cup of tea. You soak the powder in a solvent to draw out the chemicals, but you do it without using extreme heat, because that could actually destroy the delicate antibacterial compounds. Next is filtration. We're just simply separating the liquid from the solid waste. And finally, centrifugation. This spins the liquid at incredibly high speeds to separate out the different, highly concentrated layers.
Now, the solvent you use to brew this extract is absolutely critical. The researchers tested both ethanol and water. Water is great, sure, but it has high polarity, which basically means it struggles to extract non-polar chemicals. Think of how oil and water just stubbornly refuse to mix, right? Ethanol, on the other hand, has dual properties, and as we'll see, this makes ethanol exceptionally good at dissolving a much wider range of the complex antibacterial compounds hiding deep in that rind.
Okay, now that the green extraction is complete, it's time for the ultimate test. Does this liquid actually kill the bacteria that cause real-world foodborne illnesses?
Now, what's really interesting about this slide is the sheer difference in potency based entirely on the solvent you use. Phenolic compounds are incredibly well known in science for suppressing bacterial growth, and wow, the numbers speak for themselves here. The ethanolic extract yielded over 238 milligrams of phenolic content, massively outperforming the water-based extract, which only pulled out about 104 milligrams. Ethanol is clearly unlocking the heavy hitters.
And here is exactly how that chemistry translates to the petri dish. The researchers tested the extracts against 13 different bacterial strains, literally measuring how wide of a clear, dead circle the extract created on a plate of growing bacteria. The ethanolic extract absolutely dominated gram-positive bacteria like Bacillus cereus and Staphylococcus aureus. Gram-negative bacteria like Salmonella are much tougher. They have these double-layered cell walls that act like a literal suit of armor. But the ethanolic extracts still managed to halt their growth, whereas the water extract, it often just failed completely.
To get really precise about it, the researchers calculated the MIC, or the minimum inhibitory concentration. Think of it as finding the absolute minimum dose needed to get the job done and stop visible bacterial growth. It's how scientists confirm efficiency, getting the absolute most bang for your buck. And the ethanolic mangosteen extract showed incredibly low MIC values, proving they're highly effective even in really, really tiny amounts. So we know it works biologically, but let's shift back to the chemistry lab. We need to play detective for a minute and figure out who done it. Which exact chemicals in this dark liquid are acting as the assassins?
Using a highly complex profiling method, researchers identified 33 distinct chemical compounds within these extracts. This chemical cocktail contains sugars, sure, but much more importantly, it contains specific bioactive compounds like the phenolic catechin and the sterol stigmasterol. In the world of microbiology, these specific molecules are famous for their ability to quite literally punch holes in bacterial cell membranes and tear them apart.
But, having a list of 33 chemicals is just a list. It begs a really crucial question. How do we actually connect specific chemicals from that list to the bacteria-killing power we just saw on the Petri dishes?
The answer to that lies in principal component analysis, or PCA. Now, while this data might look a bit like a random constellation of stars, it's actually a highly sophisticated statistical map. Think of it kind of like a detective string board, connecting suspects to a crime scene. By clustering data points together, scientists can visually prove exactly which specific phenolic compounds are driving the antibacterial action against which specific bacteria. It takes all the guesswork out of the chemistry and provides a hard, mathematical link between the mangosteen chemicals and the dead pathogens.
So, we have a potent, natural bacterial killer sourced entirely from fruit waste. But we arrive at the final and honestly, arguably the most important stage of our scientific journey. Because let's be real, a food preservative is completely useless if it isn't safe for us to consume.
Before moving anywhere near complex mammalian trials, researchers use an incredibly clever initial safety screen, the brine shrimp lethality assay. Because these tiny invertebrates react to toxins on a cellular level in a very similar way to higher organisms, exposing them to the extract gives scientists a rapid, ethical, and low-cost indicator. It's essentially a biological canary in the coal mine. If it's toxic to the shrimp, well, that's a major red flag for human food safety.
So the crucial point is the result of that shrimp test. In toxicology, the lethal concentration 50, or LC50, is the gold standard benchmark. For plant extracts, an LC50 value greater than 1 mg per milliliter means the substance is officially categorized as non-toxic. The phenomenal news here? Every single one of the mangosteen extracts tested safely above that 1 mg threshold. They effectively kill bacteria, absolutely, but they pass this crucial preliminary safety screen with flying colors.
To fully realize this as a daily, everyday solution, more testing on actual meat or dairy products is for sure still needed. But the foundation here is undeniably exciting. We're looking at a process that takes discarded fruit peels, uses gentle green chemistry, and effectively stops the bacteria that spoil our food. For us at home, it's a great reminder to be super conscious of our own daily food waste. And it means we should definitely keep an eye out for natural, plant-based preservatives on our grocery labels in the near future. Could the ultimate solution for safe food preservation literally be hiding right there in the trash? It's a fascinating thought to chew on. Thanks so much for joining me on this explainer.